L'Hopital's rule is used when you're looking to evaluate a limit whose result initially is indeterminate, and you can't use some of the techniques that we've already learned. We're going to apply it. We applied it to one where we could use the canceling out technique, got the same answer. So the other two cases that we've learned previously were rationalization. So this is an example of a limit where we've used rationalization. So we'd multiply by the square root of 4 minus x squared plus 2x divided by the square root of 4 minus x squared plus 2x. But if we use L'Hopital's rule, what we do is we take the derivative of the numerator and the denominator and then evaluate it. So the derivative with respect to x of the numerator, which is 4 minus x squared to the 1/2 power minus 2. So we'll do that. We'll do the derivatives separately, and then we'll stick them in here. So what we'll do is evaluate the limit of the derivatives. So the derivative of this will be 1/2 4 minus x squared to the minus 1/2 power times negative 2x. So remember the chain rule. So the chain rule, you would let f of u be equal to, in terms of the first part, f of u would be u to the 1/2 power. So the derivative f prime of u would be 1/2 times u to the negative 1/2, which is that part, and then you multiply it by u prime of x. So you take the derivative of what's in the parentheses. So that's the chain rule. So let's move the square root term to the denominator and cancel the 2's out. So we'll end up with negative x divided by the square root of 4 minus x squared. Okay, now the derivative of the denominator, so the derivative with respect to x of x is just 1. So now if we plug those in here, instead of evaluating this limit, which if you let x equal 0, you'll get the square root of 4, which is 2, minus 2, which is 0, divided by 0. So what we have now is we have negative x divided by the square root of 4 minus x squared divided by 1. And now if you let x equal 0, so we're going to let x equals 0 and see if it's still indeterminate. So you'll get negative 0 divided by the square root of 4 minus 0 squared over 1, which is negative 0 over 2, which is 0. So the answer is 0. So our initial evaluation was indeterminate. But using L'Hopital's rule, our indeterminate ratio became determinate when we took the derivatives. The mistake people make is thinking, oh, there's a 0 in there, so it's indeterminate. But it's only indeterminate if they're both 0. So the other terms, this is 0, but this is not 0, and 1 is not 0. So it's a lot of these L'Hopital rule cases, the answer might be 0. So it's not unusual for examples to be 0. Okay, so I'm not going to use rationalization, but one way we could prove this is true is just plot this function and see what the value of x, what this is equal to at x equals 0. So let's do that. So we're going to show the limit graphically. So if we take the square root of 4 minus x squared divided by x, and we plot that, that doesn't make sense. Let's check, what did I do wrong here? Oh, minus 2. Minus 2, yes. I forgot the 2 part. Okay. Square root of 4 minus x squared minus 2 over x. Okay, we'll graph that. Okay, so there it is. So you can see at x equals 0, y equals 0. So that's what we would see graphically. That's what we determined using L'Hopital's rule. Okay, the third example is the squeeze theorem. So again, if we plug in x equals 0, we'll get 0 over 0. It'll be indeterminate. In this case, I don't need to do them separately because we know what the derivatives of these things are. So the derivative of the sine is the cosine, and the derivative of x is 1. So now, once I've taken the derivative, I end up the cosine of 0 divided by 1. Cosine of 0 is 1. You get 1 over 1, which is 1, which is what the squeeze theorem told us. So we used, to prove this in chapter 2 is we used geometry to look at a circle and look at different triangles associated with that circle and looking at the areas of the triangles and the segments, and we used we took the limit and we found the result was the squeeze theorem said that ratio was 1. This is certainly a lot easier to do than to go through that whole derivation in chapter 2, but it's too early to talk about L'Hopital's rule at that point. Another thing, why does it go to 1 even though the ratio is indeterminate? Because when x is small, the sine of x equals x when x is in radians. So we've used that a lot in physics. We talked about the other day about a pendulum behaving, the angle as a function of time being periodic. That was because the angle was very small, and when the angle is very small, the sine of the angle equals the angle. And the same thing applies here. When you let x go to 0, the angle is very small, and therefore they approach each other, and therefore the ratio is 1. Okay, so those are all ones that we could have done before. Now, here's another indeterminate example that we couldn't use any of the previous techniques. So the question is, what is the limit as x goes to 0 of the sine of 2x divided by the sine of 3x? And again, if you put 0 in there, it'll be indeterminate. So if we just plug it in, remember back in chapter 2 we said the first thing you do is just plug it in. So you'd have 2 times 0 and 3 times 0, which would be 0. So you get the sine of 0 divided by the sine of 0, which is 0 divided by 0. So it's indeterminate. And none of these previous techniques would work. So what we'll do is we'll take the derivative of the numerator and the derivative of the denominator, and we use the chain rule. So this becomes 2 cosine of 2x, and the denominator becomes 3 cosine 3x. So chain rule, says f of u would be the cosine of u, u of x would be 2x, derivative of 2x is 2, so you multiply, and the derivative of the sine is the cosine, so you get cosine of 2x times 2. And now when we plug in 0, so if we have a value, so let x equals 0, what you get is 2 times the cosine of 2 times 0 divided by 3 times the cosine of 3 times 0, which is the same as 2 times the cosine of 0 divided by 3 times the cosine of 0, and the cosine of 0 is 1. So you get 2 times 1 over 3 times 1, which is 2/3. So there's your answer. Now let's just plot those two functions and see what's going on. So I'm going to plot the sine of 2x and the sine of 3x and look at the behavior as x goes to 0. So if we zoom in where x equals 0, basically what happens is that the sine function near x equals 0 is linear. Those look like straight lines. And therefore, the ratio of the two, as I go to 0, the ratio of this distance to this distance is 3/2. And if I go here, the ratio is still the same because it's a line. So the distance from here to here divided by the distance from there to there is constant as I approach 0. And therefore, when I get to 0, that ratio of the two curves still maintains itself. So even though the function is not defined at x equals 0, as it approaches 0, it's like two straight lines approaching each other. So that's why you get the answer you get. 2/3. Okay. Yes?
Does this rule only apply in indeterminate cases?
I don't know. I don't know if, well, let's think of one where it's not indeterminate and see what happens. So let me, I'm just trying to think of a case where I never thought of a case that wasn't indeterminate. So I mean, if you took the limit as x approaches 1 of the sine of 2x over the sine of 3x, that's not going to be indeterminate. But it is, so if I can just evaluate that. So if all I'd get is the sine of 2 radians divided by the sine of 3 radians. So if you apply, I think the answer is no. But let's just try one example. And if you try one example, it doesn't work, then you know that it's never going to work. I mean, it's not a rule. So if we take the derivative, then you'd have 2 cosine of 2x over 3 cosine 3x. So that would be 2 times the cosine of 2 divided by 3 times the cosine of 3. And I don't think those are going to be equal to each other, but I could be wrong. And I forgot my calculator. Can I borrow somebody's calculator? Where's Lexi? And put it in radians. I don't think it makes any, well, it probably doesn't make a difference. Mode. Radians. Okay. Sine of 2 divided by the sine. And Evan probably wants to know, can we prove L'Hopital's rule, right? And that's, I said, I don't know if there's a proof for L'Hopital's rule or not. Yeah, yeah, I've never done that before, so let me look that up. Yeah, I think that's it. Yeah, so these don't equal each other. So no. Why? So the question is, how do you prove L'Hopital's rule? And why does it work? So we'll answer that question, because I don't know the answer to that question. But it's a good question. If I was only teaching calculus, I might think about those questions, but since I teach like physics and math for liberal arts and all these other things, there's only certain things that I contemplate. Okay, I have time to contemplate. Okay, now this is a different case. This is where you have infinity over infinity. So infinity cubed divided by e to the infinite power divided by 2 those are functions that don't have any bound to them as x gets large. Actually, we'll do an easier one, and then we'll come back to this one. So the same is true for this particular example. Let me just add a page here. If I did the limit as x divided by e to the x, okay, as x goes to infinity. So you plug in infinity, you get infinity over e to the infinite power, which is still infinity over infinity. So it's indeterminate. So what we do is we take the derivative of the numerator and the denominator. So this limit is the same as 1 over e to the x, because the derivative of x is 1, and the derivative of e to the x is e to the x. And now if we plug in infinity, we'll have 1 over e to the infinite power, which is 1 over infinity, which is 0. So that's the answer. So just because it has infinity involved, just as long as it doesn't have infinity in both the numerator and the denominator, you're okay. If it was infinity over 1, if we had the ratio of e to the x over x, then the answer would be infinity. Let's just do that one. So we can have zeros and we can have infinity. So if we looked at the limit as x approaches infinity of e to the x over x, that would be the same as the limit as x approaches infinity of e to the x over 1. Derivative of e to the x is e to the x, derivative of x is 1. So there you get e to the infinity over 1, which is infinity over 1, which is infinity, which really means the limit does not exist. Okay. So that's acceptable. We don't accept indeterminate. Okay, so now in this case, what happens again, if you plug in infinity, you'll get infinity over infinity. So if we take the derivative, you'll get 3x squared over 1/2 e to the x over 2. Again, I'm using the chain rule in the denominator. You have e to the 1/2 x. So you take the exponent, the coefficient of the exponent, which is a half, and you multiply it by the original expression. Now you still do that, you still get infinity over infinity. You're like, that doesn't work. What do I do? Well, you keep doing it until you don't have infinity over infinity. So you just keep taking derivatives until we do end up with a determinate result. So you get the limit of 6x divided by 1/4 e to the x over 2. So again, the exponent is 1/2 x, so I take 1/2 times 1/2 gives me 1/4. That's still indeterminate. So one more time, you get the limit as x approaches infinity of 6 divided by 1/4 or 1/8 e to the x. Now you plug in infinity and you'll get 6 over 1/8 e to the infinite power, which is 0, which is 6 over infinity. So that's 0. So the answer is 0. And if it was the other way around, if it was e to the x over 2 divided by x cubed, it would be infinity. Okay, so now we're going to plot those to show you what's happening here. And it all has to do with how, relative to each other, how do these functions grow as x gets very large. So if we take the two functions, which is x cubed and e to the x divided by 2, and we plot those. Now at first it looks like x cubed is growing faster than e to the x, because this is x cubed, the blue is e to the x over 2, so it looks like the red curve is growing more quickly. So you'd think that one would, in that case, looking into that particular range of numbers, you'd say it should be the other way around, that if x cubed is getting bigger than e to the x proportionally, but if you zoom out, you'll find out that it switches places. So let's zoom out in this direction. You're like, yeah. It happens. There we go. Okay, how far do we have to go? We didn't have to go that far. Let me change the I'm going to start all over again here. There we go. Okay, get rid of the pi on the x-axis. So it's around 15 or something like that. So at 15, the blue curve starts to take off, which is the e to the x, and it grows much more quickly as x gets large. And because we're looking at the ratio of those two, the difference between, or that ratio of the distance as x goes to infinity becomes very, very large. So I think I just need to zoom out this direction so you can see how as x gets really big, that the blue curve takes off like crazy and the red curve doesn't, relatively speaking. And so that's why the ratio, if we go back, if we just move this thing a little bit, that's why the ratio of this, which is the red curve, to the blue curve approaches 0. And that's why the limit works out that way. Okay. Here's another one we did. The way we solved this one, this is a horizontal asymptote. The way we solved this one, we solved it in chapter 3, section 5, I think it was, limits to infinity. And we took the ratio of the leading coefficients of the highest order terms. So that was the rule that we used previously. So we just say it's 3/2. But you can use L'Hopital's rule on that as well. So if we take the derivative of the numerator and the denominator, we'll get 6x minus 2 over 4x. That's it. Okay. So that's derivative of that is that, derivative of that is that, that's 0, that's 0, that's that. Okay, we're still indeterminate, so you take the derivative again, and you get 6 over 4, which is 3/2. So that's how you would do it using L'Hopital's rule. Again, you have to keep taking the derivatives until the expression is not indeterminate anymore. It just took us 2 times to do that. Okay, moving on here. I've got a handout we'll work on in class on Thursday if we have class Thursday. Okay, here's another one. Now, just looking at it from we looked at the previous problem from an order of magnitude. Do you think that's going to go to 0 or to infinity? As x gets large, which gets larger more quickly? Yeah, x squared, because x squared goes like this. The natural log goes like that. It flattens out. So the answer should be 0, just from our using intuition. Using L'Hopital's rule, we'll get the same answer. So using L'Hopital's rule, we'll take the derivative of the numerator, which is 1 over x, and the derivative of the denominator is 2x. And the problem people would make here is they'd cancel these x's out, but that doesn't work out because what I'm really doing is taking 1 over x divided by 2 over x. So if I simplify this thing down, it's 1 over x times 1 over 2x, which is 1 over 2x squared. So now if I let x go to infinity, I end up with 1 over 2 times infinity squared, which is 1 over infinity, which is 0, which is what we thought it would be. But again, if you plot those two functions, for you guys who've forgotten what natural log looks like, if I plot that, and you don't have to zoom out to show this is true. So if you take the natural log of x and x squared, you'll see that x squared grows quickly, and the natural log drops off, and therefore the blue curve is going to get much higher than the red curve proportionally as you go further out in the positive direction. And so you would have expected 0, which you do get 0. Okay, so all these indeterminate forms involve single fractions. What happens if one of the other indeterminate forms, such as 0 times infinity or 0 to the infinite power? So it says you make into a single fraction and then apply L'Hopital's rule. So to be able to apply L'Hopital's rule, it has to be a fraction or rational expression. So here we have the limit as 0, x approaches 0 from the positive side of x cubed over the cotangent of x. So that's, if we plug in 0 plus, the reason we can't put 0 in is because the cotangent of 0 is infinity, so or it's undefined. So we can't have an undefined thing here. So, well, actually we can. We just get infinity. So we get 0 cubed, which is 0, times the cotangent of 0, which as it approaches 0, it approaches infinity. So we get 0 times infinity. So what we have to do is just rewrite it in terms of tangent. So the tangent is 1 over the cotangent. So an equivalent expression is going to be the limit as x approaches 0 from the positive side of x cubed divided by the tangent of x. Now I can apply L'Hopital's rule. It's still, in this case, we get 0 over 0 because the tangent of 0 is 0. So you get 0 cubed over 0, which is 0 over 0. So it's indeterminate in the normal form that we're looking at. So we take the derivative, and again, you're going to have to, well, you might not have to take, let's see what happens. So you get 3x squared. The derivative of the tangent is the secant squared, not the cotangent. So if we plug in 0, we get 3 times 0 squared divided by the secant of 0 squared. So you get 0 divided by 1 squared. The secant of 0 is the same as the 1 over the cosine of 0. So let's see. So if we can't do this in our calculator, but if we take the secant of 0 radians, that's the same as 1 over the cosine of 0, and the cosine of 0 is 1. So the secant of 0 is also 1. And so the answer is 0. And again, if you plot x cubed versus the tangent of x, let's look at the relative sizes of those functions as x approaches 0 and see if we can just graphically kind of figure out what's going on. So we'll have x cubed and the tangent of x. And we'll zoom in. So what you can see is that the red curve, which is x cubed, is going to be very small relative to the tangent of x, which approaches it in this form. And as you get closer and closer to x equals 0, this thing flattens out even more. And so when you have the ratio of x cubed over the tangent of x, it goes to 0. Because the size of this, which is the x, the y coordinate to this, gets smaller and smaller and smaller. Okay, so that's what's happening graphically, which agrees with what we got from L'Hopital's rule. And the last one is this one that we're going to look at today, which is what is the limit as x approaches infinity of x to the 1 over x. So if you plug in infinity, you'll get x, which is infinity raised to the 1 over infinity, but 1 over infinity is 0, so you get infinity to the 0 power. So how do we that's not even a ratio. So how do you deal with it? Well, you use use the properties of logarithms like we did in chapter 5. So you can't immediately make it into a fraction, but you can only use L'Hopital's rule if it's a fraction. So we have to find some way of making this into a fraction. So let me add a page here. So let's say we'll say y equals the limit as x approaches infinity. It doesn't have to, it's not the y coordinate, it's just a y variable. So here we are. So if you take the natural log of y and the natural log of the limit as x approaches infinity of x to the 1 over x power, what that does, we can take that inside the limit. So it's a limit, and it's x approaches infinity of the natural log of x to the 1 over x. So use the properties of logarithms, and you'll get 1 over x times the natural log of x. So this is your exponent. You bring the exponent out. So now I can use L'Hopital's rule on this side. So it's still indeterminate. You can see that even when I've applied the natural log, I still have an indeterminacy, but now it's infinity over infinity. It's not an exponent, but it's now a ratio. So because I have natural log of x divided by x, I can use L'Hopital's rule now to evaluate the limit. So the way I would do that is I take the derivative of the numerator, which is this, so I get 1 over x, and the derivative of the denominator is 1. So that becomes the limit as x approaches infinity of, if I plug in infinity now, it's not indeterminate anymore. So by using L'Hopital's rule, I've removed the indeterminacy of this, and I evaluate the limit, which is 0. So it says the natural log of y is equal to 0. So y is equal to e to the 0. So I take e to the natural log of y and e to the 0 to solve for y. You get y equals e to the 0, which is 1. So what we can say is that the original question, what is the limit as x approaches infinity of x to the 1 over x? It's equal to y, which is 1. So that's the answer. So you kind of have to, I'm not going to put on a test. You probably have a homework problem that's similar to this. But if you ever end up with something where the indeterminacy is associated with the exponent, then you can use the properties of logarithms to make the exponent become part of a product, and then have a ratio of terms, f of x over g of x. Applied L'Hopital's rule, and then go back the other direction to solve for y, which is the original limit question. And then you get the answer. So let's look at that function. Just if you look at x to the 1 over x power, we'll graph it and see if it actually does equal 1. So you have x raised to the 1 over x power. Graph that. So that's what it looks like. I don't know what these little dots are. That's weird. But when the domain is greater than x greater than 0, you can see if I zoom out in the x direction that the function e to the 1 over x approaches 1, which is what we got using L'Hopital's rule. So we confirmed again that it works. And there's your homework for section 7. So like I said, we'll do an in-class practice on Thursday. So this is not the last time you'll see it, but I think you just need some practice yourself instead of me doing it. But I forgot, I didn't have time to make copies today, so that's why we're not doing it today. So we're going to move on to section 8, which is the last section in chapter 8. So I wonder what time, usually I'll see where we did this last year, I can't tell. But if you look at the dates on my previous years, 2016 we finished this on the 21st of March, which is about right now. The year previous to that, we finished on the 9th of March. That was pretty early. Here, the 4th of March. So what happened between 2015 and 2016? I think I just spent more time going through examples relative to trig substitution. So that's why I adjusted my teaching to reflect what I thought were students' issues with this kind of material. I do read your reviews and sometimes actually do something different. So, I don't know what happened to last year. I didn't have anything I did cover the material last year. But, okay, so the last section is called improper integrals, and that's where the limits are, one of the limits may be infinity, or where the function goes to infinity. And for most cases, it's not really that much different than what we've been dealing with. We do have to use L'Hopital's rule in a few special cases, but for the most part, we don't have to use L'Hopital's rule. And these involve definite integrals. So what I've got here is I asked the question, what is the integral from x equals 1 to x equals infinity of 1 over x squared dx? So if you plot the function, it looks something like this. And so the definite integral is the area underneath the curve. So you've got the area, and it gets smaller and smaller and smaller, but this little sliver goes out to infinity. So you think no matter how small that function gets, that the area underneath the curve would be infinite because one of the dimensions is infinite. But it turns out that's not the case. Sometimes it is infinite and sometimes it's not infinite. And it all depends upon how quickly this reciprocal function approaches the x-axis. So the higher the exponent in the denominator, more quickly it approaches the x-axis. Let me just demonstrate that by plotting a couple of reciprocal functions. So if I go here and I plot 1 over x and 1 over x squared and 1 over x cubed, and I look at it like that. Okay. So the red curve is 1 over x, and the blue curve is 1 over x squared, and the green curve is 1 over x cubed. And if I did the same integral from 1 to infinity, you can see that the red curve is the area is going to be larger because it's higher up. But at some point, if that curve doesn't approach the x-axis quickly enough, then you do have an infinite area. But if it approaches it fast enough, then you have a finite area. It turns out 1 over x cubed has a finite area, 1 over x squared has a finite area, 1 over x has an infinite area. And if you did 1 over x to the 0.9 power, it'd have an infinite area. There's a point here when the exponent is greater than 1, greater than or equal to 1, then you have a finite area. When the exponent is between 0 and 1, then you have an infinite area. So if I had 1 over x to the 1.0000000000001, that would have a finite area. But x to the 0.999999999 would have an infinite area. So there's a fine line between infinity and not infinity. Okay, so that's kind of the general concept here. So the one thing we do, some people kind of think, why do we do this? Because it seems like I can just use infinity as a limit, as one of the limits of integration. And you can still get the right answer by doing it. But we'd like to rewrite it. So anytime you have one of the limits being infinity, you want to rewrite it as this. It's the same result. And the reason is because the definite integral, if you use a number b instead of infinity, so b is a finite number, then you should have a finite area under here. But when you take the limit as b goes to infinity, then what you're doing is you're applying the limit to a algebraic expression, not to the limit. So this gives you an algebraic expression involving b. And so we're taking the limit instead of having the definite integral with an infinite limit, we're going to want to do it this way. It's just better mathematically to do it that way. Like I said, you can still get the right answer by doing it just by using the upper limit as being infinity. I'll do it both ways just to show you that you do get the same answer. But I do expect you on the test to do it this way. Okay, so once you have rewritten it in this form, the first thing you do is you do the integral of this expression. So that's going to be the integral from 1 to b of x to the minus 2 power dx. That's just to rewrite it in exponent power form here, x to the n. Okay, now we can apply the rule where you add 1 to the exponent, divide by the new exponent, draw a straight line to show your limits, then you plug in the upper limit into your expression. I'm going to put a little bracket here. And remember, this is 1 over, so this is the same as negative 1 over x. So I'm going to actually do that. So I'm going to have negative 1 over b minus negative 1 over 1. So all I've done here is I've rewritten this as negative 1 over x. And I plugged in the upper limit, which is b. And I subtracted plugging in the lower limit. Okay, now the last step, well, before the last step, is just to clean this up a little bit. So you get negative 1 over b plus 1. And now we're plug the numbers in, which we can do directly here because it's not indeterminate. So we'll end up with negative 1 over infinity plus 1. But 1 over infinity is 0. So the answer is 1. So, interestingly, the area underneath this curve, 1 over x squared, when you integrate from 1, x equals 1 to infinity, is 1 unit. And you can kind of see this. This is 0.5 units here. This is 0.5 units here. So this is going to be 0.5 times 0.5. So that's 0.25. And this one is going to be a little bit less than 0.2. You could add those up and kind of estimate them, and you can kind of see that they'd approach 1. So that's if you use the limit. So I'm just going to show you if I ignored myself and did it, the way that you might be tempted to do it is just say, I don't need to do that. So in that case, you would say the integral from 1 to infinity of x to the minus 2 power dx. So you'd add 1 to the exponent, divide by the new exponent. Here's my limits, which include infinity instead of b. That's the same as negative 1 over x. And now you plug it in there, you get negative 1 over infinity minus negative 1 over 1, which is 0 plus 1, which is 1. And you get the same answer. You get 1, okay? And, so it's a subtle thing here. You're not going to get the wrong answer by not doing it this way. I'll have to read it again. I forgot the exact wording they use, why they say they don't like you to have a limit for a definite integral. I think it's just because it could be an infinite area, and so they just don't like infinite areas for definite integrals. So let's do one more before we call it a day. Let's do 1 over x, which I told you wasn't going to work, but we'll show you why it doesn't work. So if we integrate from x equals 1 to infinity of 1 over x dx, again, you'll take the limit as b goes to infinity of the integral from 1 to b of, in this case, x to the minus 1 power. So I went ahead and changed it into the limit form and rewrote this with the negative exponent. So we add 1 to the exponent. Well, actually, we don't do that because it's the natural log. Sorry, that doesn't work. So we'll just leave it as it was. We'll just change it so that there's so it's still 1 over x dx. I got carried away here. So when you integrate that, you get the natural log of x. So we get the natural log of the absolute value of x and evaluated between 1 and b. Then you evaluate that, so you get the natural log of the absolute value of b minus the natural log of the absolute value of 1. The natural log of 1 is 0. So again, by plugging infinity in here, we don't get an indeterminate result. So you'll have the natural log of infinity minus 0. That's 0 because the natural log of 1 is 0. But the natural log of infinity is still infinity. So what we can say, therefore, the integral from 1 to infinity of 1 over x dx does not exist. Even though the integral of the integral of 1 over x to the 1.00001 power does exist, but the 1 over x to the first power does not exist. And it's because when you take the limit of this expression, the natural log of infinity is smaller than infinity, but it's still infinity. So it still does not exist. Okay, so that's it for today, and we'll see you maybe tomorrow, maybe Thursday. If it snows tomorrow, I will grade the physics test tomorrow.